Hello students. So today we shall learn about a very important nature of bitwise operators. Bitwise operators are a special category of operators in Java language which work upon not on exact value, it works upon the bits of the values being stored. Now bitwise operators, they work upon the integer family. Integer family means they work upon byte, they work upon int, they work upon short, and they can work upon long variables. Now if I declare any variable of this type, I can make use of bitwise operators. What bitwise operators are? They are AND operators, that is OR operator, there is exclusive OR operator, and then there is a category of shift operator that is called as right shift, left shift, and there is one special right shift that is called as unsigned right shift. I'll just explain what these operators are. And yes, of course, there is a complement operator. We know that the AND OR operators, they work on the theory of AND and OR gates. These are not equal to the logical operators which we have learned in the last video. This AND is a single AND, this is a bitwise operator, and this works in a different way. A logical AND was giving you an output of a boolean value, and that was working on boolean variables. But this AND will work upon byte, int, short or long operators. So let me show you through example each and every category of bitwise operators. So let me declare a byte variable to show you the example. So if I am having a byte I is equal to 10 and another variable j is equal to 8. Now let us see the output of each and every operator over these two variables. Once I operate any of these operators over these two, they work like this: I and j. So friends, in order to evaluate this I and j, we must know the bit structure of I and j. So we must understand how a decimal value is converted into a binary value. We need to understand the binary nature of a byte. So I tell you conversion of decimal to binary. It's very simple. I'll tell you a shortcut way of doing it. How to get the binary of a decimal value. If you need to do it, you just start writing 1 and start multiplying it in the left side by 2. It is 2, it is 4, it is 8, it is 16, it is 32, it is 64, it is 128. This is exactly 8 bit structure I have just written. What these are? These are called as the weights of each and every bit in a byte. So I am basically representing a byte by the weights of each bit. So if any bit is written 1 or 0 under it, how they can be evaluated? Now for example, I need to check what is the binary of 31, for example. So what we'll do is, we need to find out those weights in this category of 8 weights whose sum is equal to 31. Like for example, if I try to do it like this, of course we'll be using all these values which are less than 32. So 16 plus 8, it is 24. 24 plus 4, 28. 28 plus 2, it is 30, and 1 is 31. So that means if I make all these bits as 1 and other bits as 0, this will become exactly 31. I tell you a more shortcut of doing it. You know, a very good magical figure comes in. You just remember this 64. If this is 64, the sum of all remaining 6 bits after it will become 63. You start doing it from this end. You give it 2, the sum of all the right side bits is equal to 1. You take it 4, the sum of 2 and 1 is 3. You take 8, the sum of 4, 2, 1 is 7. You take 16, the sum of 8, 4, 2, 1 is 15. You take 32, you just saw it was 31. So if it is that 128, the remaining all bits are 127. So you can use this methodology in order to calculate the binary of any integer value. So in my case, it was 10 and 8. So how can we make 10? It is 8 plus 2, very simple. This is 10. All of the bits will become 0. What is 8? 8 is this 1. All of the bits will be 0. So what we get in that, we are left with only these two 8 bits in order to evaluate this. So let us write these structures here. 1, 0, 1, 0, and then 0, 0, 0, 0, 1, 0, 0, 0. If I AND this, what will happen? This will become 0, 1, 0 is 0, 0, 0, 0. So 1 and 1 will be 1 because AND gives 1 only when both of the bits will be 1. All other bits will be 0. So what is the output? You can just use the same formula to calculate what decimal value it represents. So 1 comes under 8, so it becomes 8 only. So the output of I and j will become 8. So if I do, this is AND. So what if I make OR of I and j? It will become 0, 0, 0. 1, 0 is 1 here. 0, 0, 0, and 1 and 1, 1. And all other bits will be 0. So what is the output? In this case, it will be 10. So I or j will become 10. I and j will become 8. What in the category of complement? The complement does, it changes. It is a unary operator. It works over a single operand. Like if I can write, what is the complement of I? It's called as tilde operator. So complement of I will complement each bit of this I. So it will become 1, 1, 1, 1, and then 0, 1, 0, 1. Just check it. And what is the value that we get in? This is a very important value, and I want you to just imagine how well I can determine the decimal value of this. So let us see what it gives us. Let us check system.out.println and complement of I. So let us check these two values. Isn't it amazing that you have found a negative value which has come out when I complement this I? So that means this value that I just calculated, this is equal to minus 11. How come this is true? How come it is becoming minus 11? So that is the one thing that I need to understand before I understand these shift bits. So this is exactly the nature of negative numbers I want to explain. Let's come to our program. Let us check the nature of negative numbers. A negative number is stored in 2's complement form. What is 2's complement form? 2's complement is 1's complement plus 1. You need to calculate the 1's complement and add 1 to it so as to get the 2's complement of any number. So let us see what happens once I get the 2's complement of 10. So in the last example we are seeing, so 10's binary comes out to be like this. So what is the 1's complement of it? 1's complement of it is 1, 1, 1, 1, 0, 1, 0, 1. Add 1 to it. Once we add 1 to it, what you get in? You get 1 plus 1, 0. It carries 1. And 1 plus 0 makes 1. And then all 1's. You need to know the binary addition before doing it. So this is what that we get in after we get the 2's complement of 10. That is 2's complement of 10. We know we were answered as minus 11 once we get the 1's complement of it. That means this value resulted minus 11. So how come it is true? You know, when we get a binary structure of any byte, we just listen to this leftmost bit. So if this leftmost bit is 1, it shows that the number is negative because byte is a signed value. So any number which occurs, which takes 1 as the leftmost bit, is termed as negative. So if it is negative, how to calculate its value? So we just write this number again. So because it is negative number and I need to evaluate how much negative it is, we need to calculate its 2's complement. So in order to calculate the 2's complement of it, we get its 1's complement and add 1 to it. So once we add 1 to it, we get what? You get 0, 0, 0, 0, 1, 0, 1, 1. Just write this number on the top. 0, 0, 0, 0, 1, 0, 1, 1. So this is the number that we have got. Can you guess the decimal out of it? Now, this weight is 8, this weight is 2, this weight is 1. So this number becomes 11. You know how we have reached? Let me reiterate that this number was giving us minus 11. So we need to check how. So we checked that its leftmost bit is 1. We got its 1's complement. Add 1 to it, we got its 2's complement. And now this 2's complement is exactly giving you 11. So that means any number whose leftmost bit is 1 is evaluated as its 2's complement form. So that's why it is resulting 11. So we need to remember this number 1, 1, 1, 1 and 0, 1, 0, 1. This is exactly, we need to use it for the left shift, the right shift operators. So let us see the nature of the left shift operator. Let us change the value of this I to like minus 11. Now if it is minus 11, you know we have reached to its value as 1, 1, 1, 1, 0, 1, 0, 1. How it was? This was due to like this 1, 0, 1, 0. Add 1 to it. It was giving you 1, 0, 1, 1. So this was exactly 2's complement of this number. So that means this is exactly minus 11. So if I have stored minus 11 into I, so you can assume that this I is storing 1, 1, 1, 1, 0, 1, 0, 1 in the memory. So I need to check what happens when we do some shifting operation of bits. So if I shift all the bits by 1, so what will happen? all the bits will be shifted by 1. So that means we will lose this bit. On the left shift of all these bit positions, we will lose this leftmost bit and we will be adding 0 from the right. So next number after left shift will become 1 1 1 1 0 1 0 1, and the new 0 will be added to it. The number is still negative. How much negative it is? You will have to again calculate its 2's complement, and then it will be giving you. So the output of this will be negative for sure. If you keep on shifting the bit by 1 again, then by 1 again, then by 1 again, only then this number will become positive, because this 0 will come out on this position only when we shift all these bits by 4. So let us check out the output of these two things. I am shifting this by 1, and then I show you what happens when I shift all these bits by 4. So the first output should be a negative number, and the next output should be a positive number. So let us check the output. This is the output that we have gotten. So you must have gotten and understood the nature of these variables. Now, if we check out what is right shift, we will assume that by shifting the bits by right, all the bits are shifted to the right. All the bits are shifted to the right by the number that you just specify here. So this number cannot be more than 8 for a byte, because byte is of 8 bits. If we use this operation over short, because short is a 16-bit number, so we can shift the bits by the maximum shift will be 16 to make it 0. So if we shift all the bits by 16, so all the bits will be lost and we will be left by 0 only. Similar is true with the right shift. There is one right shift that I mentioned, that is triple greater than signs. This is called as unsigned right shifts. There is a difference between unsigned right shift and this right shift. This right shift will be preserving your sign bit. So if your number is negative, so this will remain as negative. So all the bits will be shifted by 1, and the leftmost bit will always remain as 1. So that means the additions will be only on the second leftmost bit only. So all the bits will be lost, will be shifted in the rightmost direction by 1 and 1 and 1, and 0 will be added in this position. Always the leftmost bit will be negative only. So this is the operator that will preserve the negative, and this is the operator that will preserve your positivity. So if a negative number is shifted by 1, so that means on the left hand side we will always add 0 to it. So 0 addition onto the left will make every negative number as a positive number. So this is all about bitwise operators. Thank you very much. We'll meet in the next lecture.